Hello, this video is about using a 3D scanned environment or world with this external simulator for Open GPS. So here's this building. This is a local village hall called Kalmarin Nahjus, scanned here with some other things like this kiosk building here and this sculpture. This tractor is currently driving around this building, steered by this Open GPS automatic steering software. But we can also drive manually around here quite freely. And also collide to things like trees or buildings if we like. But we are not allowed to park here, so let's continue our round. Here's actually a building also, but it's not reconstructed on this simulator, so it's quite flat, only the roof visible there. Let's stop here and switch to a more sensible field because that contained buildings and such. So we'll use this field called field instead, which is actually this sports or play or multi-purpose field here. Okay, it's the automatic steering again. So the same features of course also work here as in the previous version, like this section control and automatic U-turns, and also in real installations if you have suitable hardware. This middle section of this field is actually very bumpy here. It's not that bumpy in real life, but it's related to this scanning process. We can get back to that later. But now let's disengage this automatic steering and other things, and let's drive to a bigger world through this exit here. So here's basically the world from the previous version of this simulator. It's this 1 square kilometer area with some field-like areas and such. And this new world, it's just added to the center of that. And here I used a new Godot feature called stencil buffers to filter out this bigger world from leaking into this cozy little world here in the middle. Basically, these options to modify this bigger world still exist in this version. They may make this look a bit weird because of those stencil buffers, and also this new world is now buried onto this mountainous world. if you want to use this version of the simulator to drive around on the mountainous terrain, you can also hide this new world and maybe also set this process mode to disabled, so the collision shapes and such will be also disabled. So let's get this back to enabled and or inherit, but in this case it's enabled. Check other things here. And also set this terrain back to flat. If you wondered why this tractor doesn't have a gap, it's because this simulator was actually first time drivable on the gathering for capless vehicles that was held on August 2025 on this exact location here. So the gap had to go. Here's how the simulator was set up there. So there was this 42 or so inch TV showing the simulator. The control devices were here. Pedals were also here on the floor, not visible in this picture, but there they were. And this tablet was running OpenGPS, and it was connected with this Ethernet cable to the laptop here, running the simulator. And here were some notes or instructions to the driver, like what happens from what key and such. And here on the co-driver's side were these two screens just mirroring the views of these, so it could be better seen what's going on here. And this laptop was running the simulator on Godot engine, and this was actually Godot engine was actually running on Linux here, and I have been using Linux when making this video also after the initial clip where OpenGPS was also running. So let's continue with it. And since we now have this Godot project open here, let's check those trees. In that gathering for capless vehicles, these trees were actually these high poly versions, but for this version I changed them to low poly versions because these are quite heavy to draw. So especially if you have less powerful GPU, these may cause some stuttering and lower FPS. So let's change them back to this low poly version. So these are much faster to draw. These trees around this area, these are actually identical with these front yard trees. They are just 2000 trees randomized to the approximate area of the real forest here. They are rotated and scaled randomly to make this forest look more natural. The 3D scanner used to scan objects and terrain in this video is pretty much the same as described in a another video on this channel. There's a link to that video in the description. In this case I used u-blox X20 receivers instead of F9Bs, though also the baseline or distance between the base and the rovers in the scanning rig here is about 3 kilometers, which is much longer. But let's take a look at some of the point clouds from the scans. Here is a heavily simplified point cloud of this area collected when scanning all the things here. This point cloud only has about 10 million points, and amount of the points collected total was like 400 million points, so this has less than 3% of the points collected when scanning. You can also see some trees and such here that were not reconstructed on the simulator, and also this building here, the backyard, it was quite flat in the simulator, and also these power lines and poles, these were not reconstructed at all in the simulator. About the bumpiness of this field, let's switch to this view. It's mainly caused by lack of points here in the middle section, and that's because I just walked once around this field. Basically the LiDAR units following this yellowish line here. So any points collected from the middle section were measured quite far away and shallow angle. And this field having grass caused also some inaccuracy, because some of the points were collected from the grass and some from the ground and such. So even these few points are quite noisy here. Here is also like football goals and such here. They were not reconstructed on the simulator. And here you can see this bumpiness quite clearly in this reconstructed surface. And this surface was reconstructed from these points. These are basically the same points as here, but buildings and trees removed, and all the normals are pointing up. So the algorithm can better reconstruct this surface from those points. And this also has these textures. These are taken from pictures taken from a drone. I tried to take the pictures straight downward, so it's much easier to map them here. But still, as said earlier, are some discontinuities and such here, and also this flagpole is projected onto the ground, and yes, also these trees are also projected here on the ground. So I just didn't take enough pictures to cover all angles here. So that's one one lesson learned from this project. Here are the points collected when scanning the main building. So here are close to 30 million points here. As you can see, there are not many points measured from the roof. Some points are measured from the chimneys and such here. But on this side, there are almost no points at all measured from the roof. It's because I walked around this building quite close to the wall and basically the LiDARs couldn't see the roof at all. So you should raise the rig quite high to get points from the roof, or climb to the roof with the rig, but couldn't really recommend doing that. Or use some crane or something to raise it. But we can live with these points also. And here are some points measured through these windows. Here's hall inside the building here, and these points are measured from the ceiling and back wall of that hall. So basically these points are quite useless when reconstructing the surface, but let's see anyway how it works. This takes a while, so I will skip the video. And here are the reconstructed surfaces. As you can see, this building is inside this quite funny looking cave. Walls are actually quite good looking, but otherwise this can't be really used as a model for this building. And here are some weird blobs inside the building, because reconstructed from the points there, not enough to really form any meaningful hall shape here, but algorithm tries its best. So it's better to filter those points a bit more and add some points to the roof to get a better shape. So let's see that next. Here's a bit more filtered point cloud of the building. So basically most of the points inside the building are now filtered out, and at the same time those few points measured from the roof are also removed from this. And about those roofs, it's possible to add planes to the roofs here. So here are 2 million points very closely spaced here, and also on these smaller roofs. So let's see what kind of surface we get from these points or surfaces. Here are the surfaces reconstructed from those points. As you can see, these roofs are now quite flat. But these tiny roofs are not. They are quite blobby, because they didn't have those planes defined. Especially this roof here. there was actually some tree branches very close to this roof. And points measured from those branches kind of got fused into this shape, so that's why this looks like this. There's actually this floating blob here that is also caused by those points measured from the tree here, branches. These floating blobs here are caused by the points measured from the ladders going to the roof here. We can get rid of those floating points quite easily. So now there should be only this one surface representing this whole building here. These rails or fences or whatever actually quite problematic because they were quite thin bars from up to down here, and they were like 10 centimeters apart. So there should be these holes every 10 centimeters or so, but as those points are so close to each other, it's very difficult to determine which way those are by the algorithm. Maybe some settings would help that, but now they are like this. And here are actually apparently just didn't measure points from this side of this rail or fence. So the surface reconstructed this blob here. And this model or object actually was very close to the one seen on the simulator. But this has almost 4 million faces, which is kind of excessive amount for this. There are a lot of unnecessary features like in this wall here. So the object there only had about half a million faces. But let's see the texturing process next. Texturing of these objects was done just by projecting a bunch of photos onto the surfaces of the objects. So like this my main building here, there's just a lot of pictures taken from different angles here, taken with a contraption that actually can be seen on this reflection here. So there were 3 GNSS antennas here attached to this rig with this camera also. So the initial estimate for the location and orientation for the pictures can be calculated. This can be tuned here also by hand. Afterwards, they always need some tuning, but that contraption helps somewhat to determine these positions for these pictures. You can also use some more advanced features of MeshLab to tune these, but I usually use this manual method here. The weather when taking these pictures, it was quite problematic. The day I took this, it was forecasted to be overcast, and as can be seen on this picture, this was quite shiny. Actually, it first rained, and which can be seen on some pictures like this. So the floors are still wet here. After it stopped raining, it turned into half cloudy weather. So the sun shone half of the time, and other half it was behind clouds. So these pictures are not very evenly lit. Some shadows are quite sharp here also. But let's see the final object here. Tune a bit these shading options and such. This is the same object as used in the simulator. There are some weirdness like tree branches projected onto the walls and such. This is especially weird looking here. And also some discontinuities on the walls. Basically, you could use alpha channel to mask those texture pictures, so that the texture from this wall wouldn't leak into here. As the weather was already ruining the pictures, I kind of lost the motivation and also basically run out of time when making this simulator for the gathering for the capless vehicles. So it is what it is now. And also these sharp shadows here can be seen on that particular area here, and also these discontinuities here. But well, this is what it is now. About these trees on the front yard, although these models are not based on the real trees, placement of those trees should be quite close to the real trees here. These white surfaces were reconstructed based on the points measured from this area. The trees were placed based on those. The same applies to these trees. Well, maybe this tree could be made a bit larger and this moved a bit, but maybe they are close enough. And this rail, or these rails, well, they are placed based on this rather foamy looking surface that was reconstructed from the points measured from this area. I didn't really pay much attention to scanning these rails, so that's one reason why this looks so weird. And also there was a lot of vegetation around these rails, so that's another reason why this looks so foamy. So these bars here are not just placed based on this foam to the places where they could approximately be. And this sculpture, well, as you can see, like this bar, it's much thinner in real world than it's in this object scanned surface. That's maybe partly because of these trees or branches causing some problems to GNSS signals. Therefore less accuracy on the position of the 3D scanner. So the points are not as accurately placed as they otherwise could be. And also, I don't actually remember how much I paid attention to scanning this, so that may also contribute a bit to this inaccuracy here. That's all for now. Thanks for watching this video about this experiment, and read the description for more information. Bye!